All right, cool. So today I'll be talking about the history of OCR. So I'll explain what OCR is if people aren't familiar with it. But I have been working with this technology like basically since the beginning of my career. So one of my first jobs was working for a sort of building management company. And one of the important things was we get these blueprints basically, and we want to extract all of this stuff out of it. So we wanted to say like how many sockets are there, where's the legend, what do all of these symbols mean. And so it was basically extract all the information off of these massive pages. So I've been working on this for 8 years or something like that, and I've been kind of in and out of the OCR world multiple different times. So the plan for today is kind of just I've been through this whole journey, and I want to just talk about like the major like turning points that we've had with this technology. So we'll talk a little bit about the pipelines and the architectures that people use and the data that people use in order to train these systems. And then I'll also talk about like the different evolution of like what's the best open source model, what's the like leader in terms of the commercial space. Um, and then right now, I just got hired at NVIDIA a couple months ago. And so I'm working on their OCR system, and I'll talk a little bit about like what the current modern system looks like. So that system's open source right now, so just like freely available. Anyone can play with it, but I can at least like guide through and say like here's the considerations when making that system. So just to kind of rewind, what optical character recognition is basically turning the pixels of an image into machine readable text. So you have an image of a document and it's just a bunch of pixels, and you have to say like, okay, what are all of the words on this document? And then ideally you want to understand the layout, maybe some tables, maybe something else in the document. You want to basically go image to text and then say, what does this whole page say? So this is useful in a lot of different ways. So you can imagine like you're reading license plates or check numbers or ID cards and all kinds of different stuff. So one of the ones that I've worked on multiple times is actually faxes. So you have a digital document and then you go fax it to someone and it turns into an image. And then on the other end, they want to read it and then turn it back into their database system in some way. So that is a very common thing to happen. Another one is like historical documents. You have like this old book and you want to capture it in a digital form, and then you take a bunch of pictures of all the pages and then you have to extract the text back out. So this is really, really useful for automation. Like in the past, you might have someone who actually physically reads the page and then types it all up and then says like, I'm going to transcribe this whole thing, but that's very slow and it costs a lot of human hours. And so optical character recognition is like this key technology that helps unlock a lot of text that has existed in writing but doesn't exist digitally. So this is a very important technology for many different things. Like if you look at tons of business cases, they kind of hinge on being able to read text from these images. Um, so I'll start with like what I would consider the beginning of all of these systems. So most people don't consider MNIST a OCR task, but it's kind of the first piece that was really solved out of the whole pipeline. So for people who aren't familiar, MNIST is this set of handwritten digits where it's the numbers 0 through 9, and then you have a little tiny crop and it says this is a 0, this is a 1, this is 2, etc. And then people built a bunch of systems saying like, okay, read this image and then tell which digit it is. Is it an 8? Is it a 4, for example? And so early on, this was a very powerful data set for people to have, because before this they didn't have that scale of data. They didn't have annotations at this level. So this was like 60,000 images saying all these different numbers, and then you train a system to separate these apart. So early on, people did like these hand engineered things. So like in the bottom, what you see is this is like the original image, and then you might like reduce it down to its skeleton and then like infer something based on the shape. So you say like an 8 has two loops like this and it's connected in some way in the middle. So someone would actually sit there and just think about it and say like, okay, what represents an 8? What represents a 3? What represents a 4? And so they could sit there and they could like generate a bunch of different features and say, okay, these are the different characteristics of all of these digits. But it's very hard because you have to, that maybe works for your 10 digits, but then if you want to say reach the full alphabet, then you have to engineer a whole bunch of stuff for all of these different letters too. And if you go to multilingual and everything, then it just explodes. Then it's a very hard task. Um, so eventually, I think most people have played with MNIST. Eventually, we get to convolutional neural networks, And these are a form that is very, very powerful at understanding these images. And we figure out we can find something that just learns these patterns rather than needing to hand engineer them. So we got to the point where people get very, very high accuracy on MNIST. And so that's kind of the first part that I would say has been solved out of this pipeline, is being able to look at individual digits and then say, okay, what's inside of those? So on its own, that's not very useful, because actually you go look at a page of text, or you go like look out in the real world, and you don't just have these little tiny images that just has a zero in it. You have to actually find it within the real world. And so what people did originally is they would design a form like this. So the interesting thing about this is you see along the corners, there's these black dots here. These are registration marks. And so what this tells you is like, how do you orient the page? What's the top left? What's the top right, for example? And then inside of this, you have all of these individual character level boxes. And so you expect someone to write one at a time, and then you get kind of the same problem that MNIST was. You basically say, extract out all of these boxes. We know all of their positions. And then you can just say, okay, in box one, it's a C. In box two, it's an A, for example. And so with like a very well designed form, you can make something that works, and all you need is a model that functions like the MNIST model. So you already have something that's fairly capable, and this was possible in the 80s. Like this is something that was solved very early on. So if you saw forms like this, you might see it on a check, you might see it on like a hand engineered form. You could do something like this, and it helped people extract out the information in the structured way. Um, so one of the things I wanted to show is I found this document that's just basically a guide of how you would design one of the forms like that. So this is from a company, Abby, and they're very well known in the document processing space. And so this is their written guide of like how you would build one of those things. They're like, okay, here's how you do all of the reference marks. Here's how you like here's you could add a little barcode to it, and then with that barcode you could tell, okay, this is form 17 versus form 41. And so they tell you like, here's how you design the whole thing in order to function in that way. So in reality, people don't do that much anymore, but it's interesting piece of history just to see like all of the things that they were caring about. So one of the tricks that they would do is they would say like, print the whole form in green text, and then when someone writes, they do it in black pen, and then when you do a filter on top of it, all of a sudden all that's left is the black text. So there's a bunch of little tricks that they kind of engineered into these things to make it easier to extract the text out. um, so that works great if you have control of the whole pipeline. You say, I'm going to design the form in some certain way and then extract the stuff out. But then you have this problem where the real world, people design their own documents. They go in Microsoft Word and they just type whatever up. And then you have a totally open form of, it can be any different kind of structure. And so the goal was to be able to handle like the whole range of anything that someone could possibly do. And so people started tackling the problem of like, how do we do this in a more generic way? If we don't have control of the form, how do we extract text back out still? And so one of the early tricks was this maximally stable extremal regions. And what this is doing is basically it's sweeping through thresholds and seeing which regions stay kind of stable and constant. And so on the right here, this is actually a black and white document, and the red is what it's finding are like consistent regions. And so you can see it's drawing red lines even on like just the borders of the page and some of the letters and stuff. And so there's a very like shaky method in order to just extract a bunch of blobs, and you hope these are letters, these are words, these are roughly what we're trying to extract, but you can see it's grabbing a whole bunch of other stuff too. So what they would do is they would add some custom filters on top of this. So like on the left side, you see these tall, skinny red ones. They would do something and they would say, okay, we don't expect our words to be 1 pixel wide and 600 pixels tall. So they would write a whole bunch of filters on top of this, and then they would say, okay, now this reduces down to the things that we think follow like letter-like characteristics. So this was like very early attempt at like, let's try to extract these regions out, and then we can do the same thing like MNIST style, saying like each character just try and read what it is. So one of the major players in this space throughout this whole time is Tesseract. And so Tesseract was originally a PhD project from someone at HP Labs. And so this was like pre CNN, pre a lot of the advancements that we have, and they did a whole bunch of hand engineering stuff. And so I won't even go into all of the details. It's like not relevant anymore, but they went through all of this crazy like struggle just to get all of the different pieces to work. So like they would do stuff like this where they're trying to draw the top of the text line, middle of the text line, bottom of the text line, and then try to orient that so that they have everything correctly aligned. they they do stuff with the spacing, they do stuff with chop points. I don't even know what most of these things are because it's old and it was like custom engineered just for Tesseract. And Tesseract now has gone through 5 different forms, so we're all the way on Tesseract v5. So stuff from 1, 2, 3, 4 has all been replaced now by more neural network based stuff. um, so HP worked on it in the 1980s and then kind of got abandoned, and then they just open sourced it, and then Google went and picked it back up. So the current form is still maintained partially by Google. There's not that much development going on, but it's still like one of the most widely used OCR engines. Um, so on the right here, you can see this bottom right corner. This is what their error rates were, and they're comparing like when HP gave it away to when Google picked it up and then started trying to like dial in some of the stuff a little bit more. So their error rate is about 2%, but that's on fairly easy documents. Um, so then that was on the open source side, and then on the closed source side, there's this company Abby, and I showed their little document on one of the previous slides. They've been very strong for a very long time. I would say they're not really the front runner anymore, but they had a period of like 10 or 15 years where this was like the dominant OCR engine. And so this was a OCR reading engine that introduced a lot of interesting tricks that people hadn't done before. So they had stuff with layout analysis where it was like, I have this form and it has a bunch of different paragraphs and it has blocks of text and it might have tables and it might have images, and then it would do something where it would say, okay, locate all of these different elements and then group them together. So it gave you some better understanding of how the document was actually laid out. And then on top of that, they had automatic form extraction. So in the form I was showing, they kind of engineered everything to have certain boxes and it goes with certain keys, and then they know this information happened in this specific point. So we know what that is, but it's much more difficult when you have open domain, and they introduced something that was basically like, give us any form and we're going to be able to map the key and then the value inside of that word box. And so that was very, very powerful because people could generate arbitrary forms, and then it could kind of figure out what the structure was and tell you like, this is the patient's name and then here's the like actual word that was inside of that box. um, so this technology was integrated into many different like scanners and printers and everything. If you ever took a document and put it through a scanner, it probably went through some element of fine reader. So if you got your document back and you say, okay, now it's on my computer, it probably gave you the image, but it also probably turned it into a PDF and embedded the text that it saw into it. So then you could do highlighting and like copy and paste text out of the document and stuff like that. So Fine Reader was very, very dominant for a solid period. Like they were just the most accurate. They had the most features. They got integrated in all of these printers, scanners, all of this technology. So they were a very big player for a long time. But earlier iterations, they were still using just like some custom tuned machine learning. They weren't doing any like neural network stuff because they preceded that. So they don't talk that much about their technology because for a long time it was proprietary and you just couldn't access it. So we know a decent amount about Tesseract. We don't know that much about Abby. Um, so neural networks come in 2013, 2014, and then they start just dominating, and they're shown to be so good for all of these different kinds of vision tasks. And so there's all these different custom pieces that people have designed for this OCR pipeline, and over time the neural network is swapping out for all the different pieces inside. So it's winning all of these different battles, and people are saying, okay, replace the segmenter, replace the detector, replace the recognizer, replace all of these elements that we had before, put neural networks in place for all of these now. So a bunch of the like, yeah, go ahead. Yeah, so the question was
let me just repeat the question. The recognizers that you were talking about, the previous models, they were not based on neural networks then.
no. So at the early stage of OCR, it was maybe some machine learning components, but it was not neural networks at that point. Yeah. Um, so they really took off 2013, 2014. People got much better with them. Um, and so one of the first elements that people did was they actually took this pipeline here I'll walk through. So this is an original image on the left bottom corner. And then what they do is they have a little sliding window CNN and at every position, it's saying, is this text or is this not text? And so what you get out of that is this heat map where it's saying like, oh, this looks like a letter, this looks like a letter, this looks like a letter. And so it slides across and it's just classifying at every pixel, is this a letter or not? And so you get this little heat map. And then after that, they're able to say, okay, it looks like all of these are on the same line. So they can expand it out and say, okay, this is a little line of text. Maybe it's a word, maybe it's a whole line. We'll just merge them all together. And then after that, they can do some processing on top of it and reduce it down to boxes. So now they have crops around these words, and then they can pass it to a recognizer, which will look at that crop and then say, what's the word inside of this box? So it kind of goes back to the MNIST style thing. Once you have the boxes, then you can just pass it to the model, and the model says, in this small region, what does the word say? So the first piece that kind of really got taken over by neural networks was the detection piece. So the detection is finding the word on the page. So that was the very simple approach, just saying, let's just slide it across the whole thing. And at every pixel, say text, no text. But at the same time, we got this wave of people are trying to use object detection systems, which are like detecting cars and people and all these other things. And then what people realized is these are very powerful for all of those cases, but we can translate it over to word detection as well. So then what these are doing is it's saying it's proposing a whole bunch of different bounding boxes and then trying to refine them in order to get accurate word bounding boxes. So instead of just doing a heat map for the whole page, it's outputting a bunch of coordinates saying like, here's the box that represents this word. So you can see at this phase, it's like, here's a bunch of potential boxes where words might be. And then it does some filtering. It's saying, okay, which of these actually probably has some words in it? And then it merges a bunch of the overlapping ones together. And then it does a regression step where it's trying to refine the boundaries of the box in order to better fit the word. So we get something that looks like this eventually, where it does a bounding box around the word Marriott. So we get all of the benefits of this object detection train is going on, and then the OCR world adopts it and gets a lot of the benefit. So one of the things that's very difficult with this is there's not that much data available for these systems. So people haven't gone and drawn bounding boxes for every word on a document and said, what does this word represent? And so what people figured out early on is that we need some way to kind of like synthetically generate a whole bunch of data for us to train these models from. So if we generate it, then we know where the word was placed, we know what the word says, and then we can like generate a whole bunch and then learn the like backward process in order to go back to text. So one of the first approaches was just at the word level, basically taking a dictionary and then saying, generate a whole bunch of the words from the dictionary in different fonts and different colors and different conditions, and then saying like, okay, now we have thousands of examples of all these different words in rotation and different augmentations. And then we can train a model in order to look at these crops and then classify them into the different words that they are. So there's kind of two interesting aspects to this. So the synthetic data generation, very powerful because you can just scale this up and just have hundreds of thousands of examples very quickly. But the other thing that was kind of brilliant about some of the very old research was they did this scraping attempt where they went to Flickr. So Flickr is this website that hosts a bunch of pictures, and one of the things that they did was they went to the certain typography category, and then they scraped out like often the titles would say like this word in a certain calligraphy or something like that, and they were able to gather a whole bunch of data like this and then kind of loosely label it just based on the titles. So the two different paths were like, let's go scrape the internet, and then one of them is like just generate data for yourself. So it kind of broke into two different paths. Um, so one of the interesting things about this early system was they took this dictionary and they said, okay, we have 90,000 vocabulary, but the way that they broke it down was they had it just do 90,000 different classifications. So it has 90,000 different words that it can output, and it outputs the whole word at a single pass. So current systems function slightly differently. This is a very strange way to do like 90,000 different classifications at once. And if it encounters a word outside of that vocabulary, it just can't output it at all. So, like, for example, down here, they have the word guitars. If guitar without an S wasn't in your vocabulary, you just can't output that. So it's not a very flexible system, because if you encountered like a license plate number, you're not going to have every single license plate number inside of your vocabulary. So it makes it quite difficult to like extrapolate to all the different scenarios that you would want to. So here's a breakdown of just the scale of the different data sets. So at the time, the big like academic data sets, trying to see like how good are we at doing these recognition tasks, you can see the like true hand labeled ones. This is only 50 different words, 860 different images. Here's 860 words, 860 different images. So that makes it very, very difficult, because if each of your images has a different word in it, then they're all entirely separate. So you only have one example of every word, which makes it very, very sparse. And so you can see like all of these hand labeled ones are on the scale of like the max is 3,000, but when we synthetically generate, we can have 900,000, and all of a sudden we actually have a quantity of data that's large enough to train a valid system. So I'll kind of just review the different stages of the pipeline. So the part that we looked at the beginning, so originally people were calling it segmenting, and then eventually when it kind of merged with object detection, people started calling it the word detector. And so this detection module, what it's doing is it's just locating the words on the page. So it's drawing a bunch of bounding boxes and saying, here's the word cat, here's the word table, whatever. And then optionally, what a lot of people were doing was some form of text rectification. And so what this means is they found a bounding box and maybe it's a little bit sideways or something like that. They do a step just to correct it to make it so that the words are always flat. So if the word's 90 degrees, if it's 15 degrees, whatever, they might do some step in order to like unrotate it and then make it so that the word recognition part always sees the same thing. So the word recognition part is looking at the crop of the text, and then it's saying, what's the text inside of this bounding box? So this is kind of the typical modern pipeline. The middle part might be optional. You might have other things that are mixed in, but the core parts are the detection and the recognition.
How did we go from like the 90,000 classifications to more flexible? Like, did we do like syllable classification or something, or
Yeah,
grouping?
yeah. I'll talk about it in the next slide. Yeah, yeah, yeah. So I'll get to the recognition on the next slide, but the next piece I'll talk about is the detectors. So we saw on the previous slide, they're drawing bounding boxes, and those are actually very effective, but it's kind of difficult because text can take many different forms. So if we look down here at the bottom, there's the Manchester United crest, and they've got this curved text that's going around a path. if you tried to approximate this with the detection box, all of a sudden you end up with something like you have to make the box really huge, or you have to break it into sub boxes and kind of curve around. So what people figured out is it's useful to do that sort of heat map, segmentation map approach that we saw at the beginning. So what people started doing is they kind of merged the two approaches together. They said it's useful to have a heat map because it's very flexible in case the text is like weird perspectives or curved or anything like that. But it's also useful to have the boxes output because that gives you a clean rectangle to pass to your recognition system. So one of the big innovations was just doing kind of the merging of these two approaches, the segmentation and the detection. So the recognizer is the part that you were just asking the question about. So the big dominant player here for probably 10 years was this convolutional recurrent neural network. And what this system is doing is it's outputting a single character at a time. So that makes it much more flexible than if you're doing one word all at once. So the way that this works is you have this input crop. So this is a little box that came out of the detector. And then what you do is you do a bunch of convolutions on top of it. And then what that will do is it will cut different regions of the image into these little feature sequences. So if we look over here, here's one piece of the feature sequence, here's another piece. So all of these like vertical rectangles. And what the model is doing is it's taking all of these and then it's passing it to an LSTM and it's trying to output a different character for each of these positions. So it's outputting a character guess here, character guess here, character guess here. And if we look at this, it's pretty difficult because if you were to just look at this individual region, which letter would you guess is right there? It's just blank space. And then if you got this one, you're only seeing just the corner of the S. So that's actually a very difficult task to do. So the good thing about the bidirectional LSTM is it's able to look at the whole sequence of it and just kind of piece together the picture again. But it has to output letters at every space. That's the way the system is constrained. And so you can see when it outputs in the first position, it might say, okay, I don't see anything. This is just blank space. And then at the next space, it might say, okay, I'm starting to see the beginning of an S. And then after that, it says, okay, I see a little bit of space here. And then it does a space. And then after that, it does T and then a space and then AA, because it might have multiple different cuts that C and A. And so there's a very messy way to do things. You're outputting like all of these different little chunks of letters. And then after that, you need to condense it back down into your final prediction. So this was using what's called the connectionist temporal classification loss. So this was something that was borrowed from speech recognition. They had this problem where they're trying to go from like audio to text, but the problem is they transcribe it at like the clip level, and then you can't align it for like this specific segment of audio where they started saying the CH sound, for example. It's very hard to do that alignment on audio. And so this got adapted over to the recognizer side. So they said, we can output a similar, like, here's all of the different pieces, and then we condense it down and we try to align it with what the label actually was. So this was very, very powerful. This was very good for the time, but you can see it's like pretty messy to do that mapping between the labels and the predictions, and then to actually condense your predictions down to your final thing. So there's a little bit of logic that needs to be applied to actually get the word state out of this, like all of these characters that got folded together in order to make that word. Is there a question?
Yeah, for sure. What determines the segmentation of the attention on the image? What was, is it optimally at that time, that specific amount of space for that
so
image?
these are just hard coded. It's just saying every 8 pixels or
Okay.
something like that. Yeah.
So for them, it was every 8 pixels, the optimal level of segmenting an image towards that. Okay.
Yeah. So ideally you would be more flexible than that, but that's just how the system was designed. So It's just saying we're going to make it 32 pixels tall and we're going to make all of them 128 pixels wide, and then we're just going to cut it up into slices, basically. Just uniform slices. So this was very powerful for the time, but you can see it's kind of like difficult to the model's looking at nothing, and then it has to kind of like piece all of these things together. And then at the back end, it also needs to map together this kind of mess of predictions, needs to get condensed in some way and compared to the labels.
Right.
Yeah.
Super quick comment. You said is borrowed from speech recognition, and I don't know like if there's been advancements in the last year, but as of like about a year ago, that's still what they were doing in speech recognition. So they just predefine like say 1/12 of a second, and they're just chopping it up. And so you get somebody who talks really fast, and you get phonemes maybe every 12th, but then you have somebody who says like really slow, and then like inside the model you actually see oh, and it has to decide like when to collapse those together. And it's tricky because like in English you can actually have like double letters and things like that or whatever. So but yeah, you just start with a fixed thing. You don't know if the speaker is fast or slow, or in this case, if the text is wide or skinny or whatever. And you just, the smarts of the algorithm is saying, oh, it's more likely that this is somebody talking really slowly. All these O's come together as one rather than it being, but it's possible somebody could actually, type like for dramatic effect, SLOOO and put 4 O's. So at some point you have to like decide between the two.
So would there be a flexibility in using diffusion models for text in terms of segmentation? I believe, I mean, you can randomly choose how much you segment them and then train it, and then eventually it will, maybe you won't be limited by the vocabulary size. I'm just throwing some random ideas.
Yeah, so people haven't really used diffusion. So diffusion came much later than these techniques. So I'll talk about some of the more modern approaches now, and they get rid of the CTC and they get rid of the little slicing stuff. So yeah. So eventually they get rid of the slicing, so you don't really need diffusion or anything else. They just say basically pass it to a transformer, and then the transformer figures out how to group and analyze this thing at a global level. So you don't have that artificial splitting, and you don't have the CTC loss anymore. Yeah.
I was asking about the merging step, whether it's for like speech recognition or OCR. Is there like a learned module that follows up for doing the merging, or is it some kind of like handcrafted module?
The merging is done by it's just code. It's just written to say, okay, you have 3 A's in a row, condense it down to 1, basically. And then so this website here shows like you can play with this and you can type in different letters, and then it shows what it gets mapped to. So this merging is happening automatically. So it's basically saying merge repeat. So if I just keep typing O, it still stays just hello. But if I put like space O, so you can see it added the space and then it added the O. So there's just some basic logic that's been applied to say basically if you just have the same letter over and over again, just merge it down. So this is a very cool website. Distill doesn't run anymore, but they used to make these awesome graphics and explain these concepts. So this is them explaining CTC, and they're basically showing we can go from speech. So this is some waveform saying someone saying something, and then the model is going to predict at all of these different times a certain sequence. I don't know if I can make it run again, or if me typing ruined it. But basically what this does is it's outputting some sequence of letters, and then it's merging them together and then saying here's what the final output was. and they explain the whole CTC thing in detail. We don't quite have enough time to like totally dig into it, but this is an interesting little blog post if anyone wants to play with it. So we had the CRNNs, and then eventually transformers go into style, and people realize this can actually replace the CRNN, and it also eliminates that messy CTC loss. So one of the first models to do this was called TROCR. This is from Microsoft, and they did this amazing research where they basically said, okay, get rid of CTC, just do transformer, and then the model will get an entire line of text. So before we were looking at characters and then words, and then we go all the way to lines of text. And what this does is it splits it into patches. So it gets its line of text, thin, narrow line, and then it splits it up into these little patches. And then you pass it into your transformer, and your transformer can attend to all of these different pieces and merge them together. And it understands, okay, this one's next to that one. And the good thing about this is now it has this global view. So in a single shot, it can just output the text. It doesn't need to do that messy, like for every individual slice. So here with these image patches, it doesn't have to output a prediction, for example, for the top left, whereas the CRNN in the past would have. It just says, okay, look at this entire thing, and then output 32 characters or 32 tokens, and then output the full sequence, and then a bunch of padding if there's extra things here. So if we look at this, what it's doing is it's saying, okay, this is the beginning of the sequence of text, and then it's going to output the letter L, and then ICENSE. So one of the good things about these transformer-based systems is instead of doing individual characters, it can do tokens. And so this starts doing like bigrams and combinations of letters, and it understands like these are commonly co-occurring letters, so make that prediction instead of just everything one letter at a time. So you can see it outputs the whole line of text, and with this then you just go back to regular classification loss. You don't have to do CTC anymore. You don't have to worry about the alignment. You give it the whole image, and then it outputs all of the text all at once, and then you just say, was this right or not? And then you push it in the direction of being correct. So that's pretty much modern day. So now we'll go a little bit into some of the stuff that I've been working on. So I just joined NVIDIA, and I inherited this system that people have been working on for like 7 years. And it was originally designed for extracting text out of video games, but now it's been adapted to extract text out of documents. So some of the stuff inside of it is like more focused on let's pull the text out of video games. And so I'll just talk through some of the points on that. So this Nemotron OCR is based on FOTS detection. And so what this is doing is it's taking an entire page of text, and then it's reducing it down to some feature size. And this feature size is 4x smaller than the initial input resolution. I'll have diagrams on the later slides, but I'll just explain it in text form first. So imagine you have a 1024 by 1024 image, and then it goes through some feature pyramid, and it reduces it down, and then you end up with 256 by 256 by some feature amount. So it started at 1024, it went to 256, and then what it does is at every pixel, it's doing that heat map thing. It's saying, is this text? Is this not text? And then simultaneously, it says, if this was text, where's the boundary of that word? So it's saying, predict how far to the left, how far to the top, to the bottom, to the right, and then what's the rotation? So it's doing this extremely densely. So at every pixel, it's saying, is this text or not? And then it's also saying, for every pixel of that region, where do I have to go in order to find the boundary of that word? And so after that, it outputs some boxes, and those go to the recognizer. And so the way that this works is draws some boxes, and they might be rotated, they might be skewed in some way, and then it's saying, okay, align them all. So that's that rectification step, and then it gets passed to the recognizer. So one quirk about this is instead of doing the recognizer on the original pixels, what it's doing is it's doing it on top of the feature channels that came out of the detector. So the detector reduced things down to 256 by 256. And then if you say, okay, the bounding box is over here, you take that crop out of the detection features rather than from the original pixel space. So that's one quirk about the current system. The benefit of this is it gives you a little bit more global view. So you had the model look over the entire thing, reduce it down to some feature maps, and then when you take a crop, even if the crop is bad, it can actually kind of look outside of that crop because it saw whatever the detection module saw. Was there a question?
Why does it benefit from decreasing the size, having more density?
It's partially just efficiency. So if you had to do that prediction for 10,000 or 1,000 by 1,000, that's a lot of predictions that you need to make. And it also helps because you don't actually need that precise of pixel level predictions. If you do it 256 by 256, it's precise enough at that level. You just save compute by doing it in a smaller space. But also it's useful for the recognition. It gets this reduced space and then it's able to look like outside of it because of that reduction. So then the kind of interesting, strange part about our OCR system is we have this, it's called relational model, and not many people have this part. But basically what it's doing is it's taking features in from the previous section and it's trying to group things together. So it's saying, is this the next word in the reading order? Is this word on the next line below it? And then with that, you're able to group things into blocks of text, into paragraphs, into lines. You know the reading order. One of the things that I've been working on is adding multilingual support. So for Chinese, Japanese, Korean. And the interesting one that I figured out was Arabic, you read in the opposite direction. And so this relational model is actually able to learn that for you. So normally what people will do is they say, okay, here's all my text. I'm just going to sort it on the X, sort it on the Y, and then I have my text top to bottom. But that doesn't actually work that well for Arabic. So this module can actually look at it and say, okay, it's Arabic text. I need to switch the direction of these relationships now.
How does that do on like a curved text, like on the badge? Does that perform pretty well?
Yeah. So the relational model, what it's doing is it's looking at the 16 closest words. And so it has the coordinates and it has what the letters are. And so it can kind of look at it and say, do these stitch together? So it's very powerful. It's not that common and it's kind of expensive to run, but I think it's pretty useful. I hadn't seen something like that until I started working on this team. And it's pretty good. So now I have some diagrams just showing all of the different stages. So imagine you start with this document and it has a certain height, a certain width, and then it has red, green, blue channels. Then what you do is you pass it through some feature pyramid network. So in this, imagine you have like your ResNet 18 and it's going through and it goes through 4 layers and then you output some features and then it goes through another 4 layers and you output some features. And at each stage, it's reducing it to a smaller and smaller view. And then what you do is you resize them to all be the same output and just stack them together. So you have some features that are very coarse at like the full resolution. And then you have some features that are very global because you reduce the whole thing down to be 32 by 32 or something like that. So imagine you have 1024 by 1024 height and width. And then over here, you reduce it down by 4 to 256 by 256 by whatever the feature size is. So you have some backbone and it's got some internal dimension and it's like 512 or something like that. So this becomes 256 by 256 by 512. So you have a bunch of different channels that are like reduced resolution, but higher feature resolution than before, because before we only had 3 channels. So then these reduced feature maps get passed to the pixel classification part. So what this is doing is saying that like sliding window thing, basically. It's saying highlight all of the places that have words. So if we look at this, we can see highlighting the word Zeus, it's highlighting Poseidon. And then one of the errors that you can find in here is it's highlighting 12, but it's missing the 0 a little bit. So you can see it's good, but it's not perfect. But it's very useful to have this sort of heat map that's predicting all the different regions that have text. So this is kind of small. I don't know if it shows up on there, but the next step is the box regression. So if we look over here, it highlighted all of this stuff. And then at every pixel inside of this box, it's predicting, okay, I need to go 30 pixels to the left and 10 pixels up in order to get to the corner of the box. So you have a prediction here saying, I only need to go a little bit left and a little bit up. And then you have a prediction over here saying, I need to go very left and very up. So it's very dense. It's giving a lot of predictions saying, like, here's all the different positions and where I need to move. So it's very strong supervision in terms of guiding where these boxes need to go. So it's difficult to see, but there's boxes around all of these words now. So it regressed all these points, and then it said, okay, here's the box for the word. Yeah.
You're right. So the previous slide, the pixel information, that's coming out of the first model that you showed on the first slide. And then this now bounding box creating, what kind of model is that? Is that a transform?
It's coming out of the same model. So this one model has two different heads. So one of them is doing pixel classification and the other one is doing the box regression. So the first model is just binary 0 to 1. And then this one is saying top, left, bottom, right, and the rotation angle at every point. So it's really like merged, but they're side by side. Yeah.
If I understand correctly, the first head is basically doing like a simple segmentation heat map for where the words are. And the second head is for every pixel you are predicting the bounding box for the word. Like every pixel you have the 4 points for the bounding box it's within. So do you do two separate heads, or do you feed the heat map into the the second one? I don't know if that question makes sense.
Yeah, they're two separate heads. They could be totally merged, but they're functionally two separate heads.
I'm saying, like, wouldn't it be, because this might be really expensive to predict a text box regression for every pixel, would it make sense to first do the heat map and then only run that for those pixels?
You could. It doesn't really cost you that much to just output 5 extra points versus 1 for every pixel, because we're doing it in this reduced space. Yeah.
Okay.
You could filter it and say only compute it for those regions, but you also need it to make reasonable predictions even when it's outside of a word. So it's good to have that supervision everywhere.
I see. That makes sense. Yeah. Thanks.
It's wonderful talk. Thank you so much for doing it. It's actually regarding not pixel recognition, but mostly I'm looking into the vectorization. And I don't know, I was asking Ted last time, but I thought it will be much to the point if I ask you regarding some of the models. I think NVIDIA has some of the models that I'm not sure if you will be talking later, so I don't want to like repeat this question, but it's mostly regarding the searchable vectors instead of like only doing the digitalized text. And if that's actually rings a bell, so I can.
Can you repeat the question? I don't know if I heard all of it.
It's mostly about the vector embeddings instead of like doing the raw text recognition. Will you be talking about the Omni embed? I'm looking into
the Omni embed stuff. So that's the next stage after the OCR. I can talk about that at the end, but I don't have any slides specific to that. Yeah. So one of the pieces of this is it's doing this box regression and it's saying, okay, predict the top, left, right, bottom. But the other thing that it's predicting is the rotation of these individual boxes. Um, so the rotation in document context is not usually that important. So the rotation, when you have a document, typically your text is just horizontal, or maybe you have some that's vertical, and so you can kind of orient those, but you don't have that much stuff that's actually like rotated a little bit. You don't have text that's at a 17-degree angle that often. But in the video game context, it's very common. So like imagine they have these cards here and the card is just a little bit like that. So all of the text has to be crooked. So the one of the reasons for doing this originally was in the video game context is very common. In documents, it happens, but it's not that common. But that's one of the like design decisions that informed that. So the next piece of our pipeline is the recognition transformer. So what this is doing is kind of similar to the TROCR. It's receiving the output from the detection model. So the detection model created some features, and it also gave us a crop saying like, here's the specific box for this word. And then what you do is you take that crop out of the detection features, you rotate it so that it's the correct angle, and you resample it so that it's the correct size as well. So we always expect it to be only 8 feature pixels tall. But if you remember in the earlier slides, we're reducing it down by 4x. So this is 32 pixels functionally tall, but in the feature pixels, it's only 8 pixels tall. So it becomes very small, actually. And then we also resize it to be a certain width. It's always a certain width. And this is determined by our sequence length. So if we want to output 32 characters, for example, then what we would do is we would say resize it to be 8 tall, 32 wide. And then in reality, that would be 32 tall in pixel space and 128 wide in pixel space. But it's resampled, so it doesn't matter what size originally it was. So it outputs a prediction at every slot. So it can output 32 characters, for example. And what it would do is it would just basically say, okay, here's the 5 letters I need to predict, and then the rest are just padding. But it does this all in just a single forward pass. So it just predicts the entire word, and then we have some examples of this on the right-hand side. So these are the original pixel crops that came from it, and then it's outputting predictions saying, here's the word that I'm seeing out of this. So all of it's very small, but all of the ones that are marked in green are correct, and then all of the ones that are marked in white are incorrect. Yeah.
For training, do you train the recognition detection separately, or is it end to end?
It's all end to end. Yeah. Yeah. So that was when I joined this team, I was kind of impressed because the entire thing is just a single forward pass through the whole thing. So it's very useful to be able to like have detection, recognition, relational model are all using the same backbone, same forward pass. So they all kind of inform each other. So now I'll talk about that global relational model I was talking about. So this again is using a lot of the same features. So this is taking those feature maps that came out of the detector, and then it's also taking recognition features. So this can be stuff like the embeddings from the recognition feature output. It also gets some geometry. So it tells it, okay, this is top left of the image, and it's also 15 pixels away from this box and 20 pixels away from that box. So it gets the detection features, it gets the recognition features, and then it also gets geometry features, just informing like what's the relational output spatially. And then what this model does is it's another transformer model, and what it's doing is it's taking the 16 closest neighbors, and then it's doing sort of a re-ranking thing almost. So it's just saying measure, is this the next word in the line? Measure if this is the line after, and then also give me some confidence if this is on the line after. So it's looking at the 16 closest relatives and then just basically saying, is this the next word in the in the line, and is this potentially a word from the line below? And so from that, it's able to understand what's the reading order, and then also what line should we go to after once we finish this line of text. Yeah.
The relational model trained on what specific data?
So this comes from the same thing. So there's a data set called hierarchical text, and it was annotated in this way. It was actually like they annotated a whole bunch of stuff saying, okay, this word comes after this word, and then this is the new line. So one of the things that I've been messing with is synthetically generating stuff that's labeled in that way, because most OCR data is not labeled in that way. Yeah. So the model that we're training now, it's trained on 13 different data sets that have been merged together, and only the hierarchical text has that certain annotation form. And so one of the struggles that I've been running into is that was only annotated in English, and then I'm trying to add Chinese, Japanese, Korean, and then all of a sudden the model is saying, I don't know how to sort these words properly. So I've been synthetically generating data that has this sort of annotation format that's saying this word follows that word, and here's the new line and everything like that. So yeah, it's a custom labeling piece. It's kind of difficult to work with because most of them don't have it. So it's a very useful model, but like to annotate things to that level is kind of difficult to get. So with this global relational model, one of the things you can see is it draws these little lines connecting all the different pieces. So like this is kind of interesting because it's able to figure out, okay, this word draws an arrow to that word, and then you can see it might, if you just sorted this XY, it might go this word, that word, and then jump over to the next card and go to that word. But it's actually able to tell, okay, this is the next word in the sequence. We have to go down a line to this word. So it's pretty interesting that it's able to capture that more complicated relationship. So this one, it's going all the way across the line, and then it says, okay, go back to the word he. So this is a very powerful thing to have. It's maybe a little bit overkill in document context, but it's very useful if you have paragraphs and blocks of text and different like pie charts and stuff. It can kind of like traverse the whole thing and just guide you along the whole path. So I won't spend too much time on VLMs. This is definitely like the direction that things are going. But with VLMs, things go like all the way end to end. So throughout this whole thing, people went from hand-engineered pipelines to neural network-based pipelines, but it's still all of these different stages where you kind of have to supervise them in specific ways. So like the detection part, we need bounding boxes telling us specifically where the words are. And then on the recognition side, we need to know the bounding box and the actual text inside of it. And then for the relational model, we need even beyond that, saying like which word comes after which word. The vision language models, they're so powerful that you just basically say image in, text out. If you just tell me how you want to format the text, if you tell me you want to output boxes, if you tell me you want to reorder the text, if you want to have it structured in Markdown or JSON or whatever, it can just do whatever. So it's like very arbitrary input image, output text, do whatever you want. So it's very, very flexible. But one of the things that I've been running into is like it's very flexible, but it's even more data hungry. Like when you have these specific pieces of the pipeline, it's pretty simple to train a model just to do bounding boxes and just to do text to words. When you try to merge all of these together, I'm sure at the like data and compute extreme, you eventually win with the end-to-end approach. But as it is right now, it's very compute hungry to actually like get this model all the way to that point. Was there a question? Yeah.
So with these approaches, the architectures are like pretty monolithic. You don't have specifically designed sub-architectures for doing specifically like biased like purposes like in the previous ones. It's just like stack a bunch of transformer layers and just input output more or less.
Yeah. So the typical flow with these is you have some sort of image encoder, and that image encoder will send some information to a large language model. So for like GPT-4o, they basically said I don't know exactly what GPT-4o looks like, but it's probably some image encoder, and then it maps some information down to like an LLM token level, and then after that, it outputs some text. And so one of the most popular models for that was called Lava, and it was basically they were the first people to really capture that concept of like, here's an image encoder, just like fuse it into a large language model, and then whatever vision information you pass to Llama in this case, just use that in order to inform your generation.
So it's like you just have image encoder and then language decoder of some kind. Maybe it's pre-trained and then you just train end to end.
Yeah. 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 So very flexible, very powerful. One of the things that I've been kind of studying is there's a recent DeepSeek OCR model that a lot of people have been excited about. And one of the things that I've realized is like people talk about hallucinations in terms of like LLM context. And in the previous like OCR pipeline, your like hallucination or just error is very constrained. You have a single word box. It's limited to, it can screw up that word, but it doesn't screw up the rest of the page. One of the things that I've seen with DeepSeek OCR and some of these other end-to-end methods is it has freedom to just hallucinate an entire paragraph. It can see, oh, you're talking about Apple, and then output a whole bunch of other stuff about Apple that's not on the page. And that's kind of a scary error mode. Whereas with the OCR stuff, it's like it read the single box wrong, but it doesn't matter if it misspelled something, but it's bad if it like just generates a whole paragraph that didn't exist there before. So I think eventually all of these things will get smoothed away, but that's been my experience so far, is like there's this kind of like hallucination problem with the OCR when you do it end to end like this. So the big power of this though is it's so flexible. So in the OCR model, the pipeline approach, you just get text out. That's the only thing that can happen. But what people have shown with these more end-to-end approaches is you're combining the smarts of this image encoder, and then you're combining the smarts of some large language model, and you're giving it full flexibility. And so what it can do is it can do translation on the fly. So you could give it an English document and you prompt it and say, turn this into Spanish, and then it will read the whole page and output just in Spanish. Or you can do summarization. So you give it a page of text and you say, just give me the key points. So it doesn't have to like output all of the text from the page. It can do all kinds of different stuff. And because of this flexible approach, it can answer questions for you. It can summarize. It can analyze charts. It can say, oh, this one's higher than that one. It can do grounding. So it can basically, you say like, tell me where the red panda is, and then it will actually draw a box for you. It can do all kinds of amazing stuff. So I won't go into great detail on these, but one of the original papers on this that I thought was really interesting was this Cosmos 2.5. And I would say it's one of the first like end-to-end systems, very powerful. And they showed we can do this in many different ways. So you could say, give you this input document, and then now I want you to output it in some layout aware way where it says, okay, here's the arrangement of all of this text, and it's putting the lines together correctly for this table down here. Or you could say, make it a markup format. So you just prompt it in different ways and you get entirely different representations of the text. But then you can, let me see if I can find examples. You can do all kinds of crazy stuff where it's even looking at charts and stuff like that and extracting all of this stuff out in some reasonable way. It's grabbing all of the different paragraphs. And so the way that it does this is it's simultaneously outputting text and bounding boxes. So if you think about the LLM form, it's just outputting tokens, but it's choosing tokens that are like here's the coordinates of this box, and then here's the word that's inside of this box. So it's very flexible, but you can see how complicated that is to do. So they have many different examples of all of the different things that it can do. Yeah, go ahead.
Is it possible to recreate the curve mathematically within the inputted graph, or
there are models that do that now. In this specific one, it wasn't able to. So there's a relatively recent model called slow perception that will actually try to extract like all of the data points out of a chart and stuff like that. So it's very interesting that people have figured out how to solve that. But yeah, so if you had something like this, it could try and say, pull out all of the data points and understand like numerically, like, okay, this one's lined up with the 2.5, for example. Yeah. But that's not what these models do yet. Yeah.
So this kind of like arbitrary output capability is just a consequence of using a pre-trained language model. But to some degree, you are fine-tuning it to work with the vision encoder to some extent. And that just works fine.
So the way that people started with these was they would take the image encoder and then they put a few layers in between to the text decoder, and they would only train that little bridge between the image and the text. And so you would say just put 2 layers in between, basically, and it's learning a translation from the image space to the text space. And so you're keeping all of the language understanding of the text decoder, and you're keeping all of the image understanding of the image encoder, and you're just saying like convert from one space to the other.
I see. So you're not like perturbing the weights of the language model by training it end to end. You are just supervising this intermediate translation.
Yeah.
I see. Yeah. Thanks.
Yeah.
So I use Python version of Tesseract, PyTesseract, and it does a good job. I mean, I get some code as in an image form, and I feed it, and it comes back with text, and the errors are consistent. So I'll know, oh, okay, this is where it will make error. So it's pretty consistent, but I use it only for a very limited application. Some Python code actually, when somebody sends it in an image form, but I have to actually copy and paste and create my Python file. So, so would there be a better package or something like that? Or this is the best in terms of if anybody understands this,
PyTesseract is pretty good when you
Okay.
have clean text like that. So if you have code and you have a screenshot of some code, it should be able to do a decent job. There are other packages. So there's some models on Hugging Face. So like this Cosmos 2.5 model, that's up on Hugging Face. So you can run it if you want. It might be a little bit more difficult than just like passing it to PyTesseract, because you have to actually like run a heavier model. But there's also DocTR and EasyOCR. There's multiple other models that have come out that in theory beat Tesseract. Tesseract's pretty good at clean images though, so it might be difficult to beat. So at my previous company, we trained one of these end-to-end models, and one of our focuses was making a small, lightweight one that you could use for a lot of documents. So the big downfall of this end-to-end approach, partially the hallucinations, but also it's very slow and it's very expensive to run for large images. So it scales poorly as you get bigger and bigger images. It scales quadratically, whereas with the like pipeline approaches, it's got CNNs that don't scale so heavily. So what we did with this model, we called it Mississippi, was we said, okay, train one of these vision language models and focus it on OCR and document understanding, and just make it as small as possible that it can still be useful so you can process a lot of documents. So the whole focus here was just basically make it small, make it decently fast, So it's good for its size, but if you compare it to GPT-4o and everything else, those obviously beat it because there's so many more parameters. But this was trying to get something that was like small enough that you could run on a phone and still get some amount of text out. So this is a few years old at this point, but I just wanted to.
Would you suggest using that one?
In the right case, yeah, I would say it's fine, but there's many other models that have come out since then. So the one that I would point towards right now, there's this Hun model that just came out. I would say that that's probably later right now. I haven't tried it, but like based on the paper results, that's probably the best right. I can. It's Yuan. It's from Tencent. Um, so I've been keeping up with all of the different OCR stuff, and this is one of the most recent releases. One of the things that I do is I keep track of like how many downloads all the different models have. So this one has been getting 1 million downloads a month, so it's fairly popular. So the other one that's been getting a lot of downloads recently is this DeepSeek OCR. So this is getting 3 million downloads a month. But my belief is that DeepSeek OCR did very well in terms of the architecture. They made it run very fast, but it's not the most accurate. So based on my reading of the paper, this group did a very good job in terms of building a very expansive data set and training it very well. And the DeepSeek OCR team did a good job of innovate on the architecture, make it run fast, make it efficient, so we can push a lot of pages per second. Yeah.
So the H2O model you showed seemed to coincide with the general architecture you just described. It seemed like there's an MLP projector that I'm assuming is the thing that you're fine tuning between a frozen vision encoder and the language decoder. What are, for these more modern models, what are the major new like changes that are being used?
So for the some of it has been using different image encoders. So that's been a lot of the progress actually, is people have just trained new like SIGLIP and SAM and all these other things. So the DeepSeek OCR model, the way that it works is it goes through a SAM model, the segment anything model, and that does local attention, which is very valuable when you have this 1024 by 1024 image. You just look at the stuff close to it. You don't have to look at like the top left token doesn't need to look at the bottom right token. And so it makes it much more efficient to do local attention. And then after that, they reduce it down 4x on each dimension. And then they pass it to SIGLIP, which does global attention. And that makes it so you kind of have the best of both worlds of you look at like a local region and then you condense it down and then you look at the whole thing all at once. And that opened a lot of doors in terms of you can have higher resolution input now, but also what you're passing to the text decoder isn't 6,000 tokens. It might be 256 tokens. So that made it so that it's much more condensed and can run a lot faster. So I would say that's like the major architectural difference. The actual connector piece is still, even in their case, just like 2 layers or 3 layers or something like that.
So like the advances are more on the individual, like the constituent components for the language, like advances on language encoders and LLMs are naturally just going to push progress on this problem statement.
Yeah.
Okay.
Yeah. So there hasn't been that much innovation on like how do we connect these pieces together. People have figured out you put some linear layers between them and it works. So that's what most people have been doing.
Just a quick clarification on the connecting them. I didn't pay close attention, but I just assumed there was a small amount of fine tuning of the language model to just understand these new vision tokens. Are you saying that you think some of them are actually truly completely frozen, no change?
Yeah. So we've done experiments on both ways, and you can actually just train the whole thing end to end, but that's more expensive to run and you can't throw as much data through. And one of the things that we experimented with the Mississippi model was unfreezing the different portions. And it can help, but you're kind of all you're really trying to do is translation from image space to token space. And so if you can learn that translation, then you don't really need anything special on top of it. But we did do experiments where you unfreeze the text portion, and it does maybe get you an extra few percent of accuracy, but it makes it much more expensive to train.
Cool, thanks. So I didn't realize that. And then, like, I don't know if you know for any of these models, like for the H2O Mississippi, does it have dedicated vision tokens or something that says begin vision or whatever, or is it truly just writing directly to the text token space?
It has a certain begin. I don't remember what it's called, but it's like beginning of images basically.
Right.
It's like this image, that image.
Yeah, and so that's the thing that's like I'm having trouble wrapping my mind around is if the LLM has never seen a begin image token, that it just figures out what to do without any, not even like a tiny fine tuning step or something. Yeah, thanks.
Other questions?
So you're saying that like if you take like a small model, like a 3 billion parameter model, right? And you just feed it the image encoder data. Like, isn't there a way to maybe create like a small model that like what you were saying that performs better at the image encoder like output step than maybe taking like these random LLMs that are kind of optimized to like respond to questions? Isn't there that the bottleneck kind of like to running these small ones? Like, shouldn't you be training like a smaller LLM?
So that's one of the things that I've been playing with. My belief is that these text decoders are oversized. Like if your goal was just purely OCR, then you don't need 3 billion parameters. Like in this case, we have the DeepSeek 3B text decoder. That's unnecessary to just go from images to text. So I think that there's strong argument for that, but one of the things that I found when training some of these models was it's very useful to have this model that already understands the like co-occurrence of words and stuff like that. I played with plugging in, I did my own work trying to say, okay, take the DeepSeek model and then put a smaller transformer decoder here. And I did randomly initialized, and then I did with Gemma initialized weights. And the Gemma one immediately is like converging so well, and the other one is like struggling very hard to even output.
Yeah, so there is something in the world model that affects like the performance. Okay.
Yeah. So it knows which words go together. It knows which tokens go together to make the words and that stuff. So it's definitely useful, but I do think with enough training, like there's not a hard requirement to.
Okay, so maybe you could like generate like a whole bunch of translations with like a large model and then kind of like train the smaller model on those outputs and try to. Has that been attempted or like?
I don't know if it's been attempted, but I definitely like my belief right now is like the pipeline approach that we're doing, we can push 100 pages per second with the right GPU, but then with these approaches, you get like 1 page per second or 3 page per second, and most of the slowdown is actually from the text decoder. So if we can solve that, that's like a huge benefit. So that's one of the areas that I'm focusing on, but we have many people working on different things. So we'll see what happens. Yeah.
Well, you talked about passing through hundreds of pages. What kind of clusters of GPUs will you utilize in order to have that kind of workload?
So for that, you can do a single like modern GPU and get 100 pages per second off of one GPU. Like that's how fast the approach can be. Like the GPUs have gotten so good that you
Like
can
an
do that.
8100 that
Yeah.
could pass hundreds of pages and finish it relatively quickly
Yeah.
within like what time of the span? Like 10 minutes,
Um,
20.
whatever the 100 pages per second and your total number of documents is. So in 1 hour you can process a lot. I'd have to do the
Okay.
math, but yeah.
Oh.
Yeah. Um, so one of the things that they mention in this DeepSeek paper is they're bragging about how much they can do on, they're saying we can do 200K plus pages per day on a single A100 40. Yeah. Yeah. So I don't know what the equivalent is on our pipeline. I could do the math, but it's much higher than that, probably multiple orders. Yeah. Yeah.
Can this be optimized if you, let's say you're dealing with published book pages and you have maybe a half a dozen typefaces and you say it's only in English, it's not going to have diacritical marks and so forth. Can these models be fine-tuned? For example, even just using something like Tesseract, can you constrain it down to be, so the usual problem is that you get an image of an old page and it's got little flecks and stuff like that that get treated like diacritical marks, and it's an editing nightmare. Are there ways to constrain this down and get some better performance and efficiency?
Yeah. Yeah. So in all of these models, they have different vocabulary to output, and you can different methods have different ways of accessing it, but you can block off certain outputs. So you could say, I only care about the alphanumeric, so only do these 36, and you could basically block off and say, you can't output any A with an accent mark or anything like that. Yeah. Yeah. So it's possible to constrain it like that. Yeah.
I think this is a bit of a follow-up on Ted's question. So when you do this intermediate projection and you're doing intermediate supervision, how do you preserve information about like the spatial structure of the image going in? If you're just converting to text, there's some level of information loss, I'd imagine, being passed in the LLM. How do you preserve that information?
I'm trying to remember if it was the DeepSeek one or something else. Maybe it was the other one. Let me see. So one of the papers, some of their work was on that representation, is we're splitting this thing into a bunch of tokens. How do you relate them together? How do you understand the position of them? I think it was this one. They have a specific, they called it 2D rope or 3D rope or something like that. But basically they had some embedding that was trying to give you, here's the position, this is a token from the top left, but then it's also trying to say, here's the ordering of the words. So it's 2D because you have X, Y, and then you also have this word after that word. So these tokens came in this logical order. I don't remember which one it came from, but there was some paper that was showing that advancement recently.
So therefore the LLM is getting like the words and then they're just their spatial positions. Yeah. Okay.
Yeah. Yeah. So one piece I'll touch on for just a second, there's this OmniDoc bench. This is a recent benchmark that a lot of people have been taking stabs at. And what this is it's about 1,300 pages that have been annotated in all kinds of different ways. So some of it is like classic OCR, but if we look at this image, they basically said, here's all these pages of documents. What's all the things that you could possibly want to do with these? So you might want to extract stuff out of tables. You might want to extract stuff out of charts. You might want to read math formulas. You might want to just like read Chinese text. You might want to read English text. So they gathered up all of these pages and they just said, we have all these different types of stuff. And then we also have all these different things that you might want to be able to do with it. So you can see we have mixes of languages and backgrounds. So you might have clean white documents, or you might have different random colors, or you might have multiple colors on a single document. Your page might be rotated, and then there's all these different things that you might want to do with it. So this is one of the interesting benchmarks that's popped up recently. So this is just some results showing like how do they do overall. So right now I would say Paddle OCR is one of the leaders. They don't have that even more recent one that I was mentioning, but we can see their size, we can see their performance on what's the text edit distance, how good are they at formulas, how good are they at tables, how good are they at figuring out the reading order of things. So all of these things are important, but lots and lots of work went into this set of benchmarks, just understanding like what are the different things that people want to do with documents. So I'll wrap up there, but the big thing is like the future definitely seems to be vision language models, but the difficulty now is like we have working pipelines that can push 100 pages per second, and then you say, okay, these models are, we know they're even more powerful, but now you go down to 1 page per second. That's not acceptable for many use cases. So eventually, I think people will figure out the optimizations in order to get that closer and closer to the 100 pages per second, or we'll get faster GPUs, or all of these things are going to happen eventually. So I think that the definite direction is going to be these vision language models. But for now, they're kind of in a half usable state.
If you think that VLMs are kind of the future for OCR, do you see the future of that being more on optimizing for the two separate pipelines, image encoding and then language model, and then just like stitching them together? Or do you see it being end-to-end training?
I think that the most likely outcome is it's going to stay relatively similar to what it is today, where people just like, we get free improvements from someone trained a better image encoder. Eventually, someone's going to train a better like custom text decoder for OCR stuff. And I think part of the battle right now is just data quantity. You need enough variety of data. So one of the things that I've been working with is synthetically generating a whole bunch of documents. But even that, it's hard to cover all of the different conditions that people can have. So I think very often what we see is like the jumps in performance isn't from some like massive leap in algorithms. A lot of it has been like who gathers up data, who scrapes, who generates, who does whatever and gets the biggest, widest set. Like what I was saying with the DeepSeek OCR, they were architecturally good, but they were not that good in terms of the data. So I think the main battle on the OCR front is data. Yeah.
Something outside of this is how do you contain information from being sent back to the creator, or say like in a security context, contain the data that you want to contain, and then whatever you want to send back? Is there that amount of finite controls within within the language model, or if you had your own custom, or you use someone else others? What are the guidelines, or how do you what step in this, could you customize this in any way you think?
There's not really much in the way of like security or preventing bad outputs coming back, but the model's only trained to just try to go from image to text. So whatever you pass to it, you'll get something back. All of these things, like all of the models that I've talked about, the more recent ones, they're all open source. So you can go inspect them and see what they're doing. And if you want to, you can go fine tune them for other things. So if you say it's doing great on English, but it's not doing great on French, you can go take it and fine tune it for that specific thing. Yeah.
Awesome. That was a great presentation, Ryan. Everybody, hands around. All right, we'll wrap up the formal part of the presentation here. A quick administrative note. So hands-on machine learning, deep learning next week. In 2 weeks, another topic. And then I wanted to make a plug. In 3 weeks, it'll be the first Saturday in February. So we're going to do our monthly event. And I'm a little bit slow, a little bit behind on this, but we're looking for speakers for our monthly events. And so there are a couple of people who responded to the suggestion form. I'll reach out to them, but also here we're open and whole wide range of talks accepted. So it could be anything that you're working on. So if you're doing ML for chemistry, or you're doing ML for aerospace, or ML for finance, whatever, doesn't matter what the domain. And also, it does not need to be cutting edge research. It's also an opportunity for people, if you want to do a lightning talk and just practice speaking, practicing for interviews, practicing for work. You can also just say, hey, I'd like to do a 5-minute presentation about a project that I did. It could be a beginner saying, I'm going to do classification of who survives the Titanic, right? It could be MNIST. It does not have to be something groundbreaking. It's just an opportunity for everybody in the community to practice, and an opportunity for people to, share about different things. So please contact me or message me on Slack if you'd be open to doing either a short or a medium or long talk in any of the upcoming monthly meetings. All right. For those of you here, feel free, if you want to chat, meet up with other people, whatever, grab some more snacks, and hope to see you guys future Saturdays. Thanks.